Hi kids! So this lecture brings in our old friend conservation of energy to talk about how it applies to waves, which are made up of energy, so it should be really relevant. If you recall from the first video, I mentioned that the amplitude or the size of the wave is representative of the wave's energy. So if you're taking a look at a transverse wave, obviously that wave on the left is a relatively low energy wave because it has a small amplitude. If you measured the height of that wave from equilibrium, the height of a crest or the depth of a trough, it would be a relatively low number, whereas the wave on the right has much more energy because the amplitude is higher. In a longitudinal wave, it's a little bit harder to picture, but what's happening here is the amplitude is demonstrated by how tightly packed those molecules are in the compressions and how spaced out they are in the expansions or the rarefaction. So in the top, these are waves in the air being made by a tuning fork or a musical instrument that's vibrating the air. And as that musical instrument vibrates, it sends out these little pressure pulses through the air. If it's vibrating gently back and forth, those waves have a low amplitude because they're not very compressed. But if that tuning fork is hit hard and it's vibrating a lot, then the wave is going to have a much higher amplitude because the compressions are going to be much more dense. Okay, so if we made a graph of a wave's amplitude over time, what would we see? So when you make a sound wave, or if you splash in the water and you follow that wave, what happens to its amplitude as that wave moves through the medium? Hopefully, it would occur to you that the amplitude starts off at its maximum when the wave is first made, that first displacement. And then as that wave moves, the wave actually gets smaller and smaller and smaller until eventually it virtually disappears and you don't see it at all. Now, given that amplitude is the energy of the wave, it sort of seems like this might violate conservation of energy because this wave starts with a lot of energy and it ends up with not very much. So where did the energy go? This is obviously not a closed system because the energy is not staying in the wave, but where is it going? Well, just like other types of energy, that wave energy is being transformed as that wave moves. It's turning into heat because the molecules of the medium are rubbing against each other. It's turning into kinetic energy if it pushes anything that's in the way. So maybe a duck is sitting at the water on the top of the water, and that wave has to put some energy into pushing that duck up and down. So the duck's kinetic energy is being sucked out of the wave. Gravitational energy, maybe it's lifting up something as it moves. So everything that happens as a result of the wave is actually taking some of the amplitude out. It's an open system and it's losing energy, but that energy is just turning into other kinds of energy. One quick note, it says up above the frequency of the wave stays the same. This is actually really important. The number of waves every second is constant, even though the amplitude is decreasing. We're not actually losing waves, okay? You can't gain or lose jiggles. The number of waves every second is set by how fast the wave source is vibrating up and down. And, we can't have a person like kicking water 10 times every second at the other end of the pool. Even though those kicks aren't nearly as large amplitude, you're still going to feel 10 waves every second. We can't gain or lose those kicks. So as a wave moves through a medium, or even if it moves into another medium, the frequency of the wave is going to be staying the same as it moves. Speaking of waves going into other medium, when a wave hits the boundary between two different media, something kind of interesting happens. The energy of that wave actually divides. And some of that wave energy is being reflected back to the medium that it started with, and some of that wave energy is being transmitted into the second medium. So in the picture below, we have this beautiful bubble, and obviously some light waves are hitting that bubble. And when the light hits the bubble, what happens is some of that light travels through the bubble, and you know that because you can, the bubble's transparent, you can see through it, and light would shine through it. But you can also see that some of that light is being reflected back because you can actually see the reflection of the world and the light coming from behind you in the bubble. So you're actually getting some of that light bouncing back to you. So the wave energy that hits this boundary between two media, in this case it's air and the bubble solution, actually splits that wave energy into two parts. Now obviously the amplitude of each part has to be smaller than the individual original wave because of conservation of energy. So with a wave that's going through that bubble has less amplitude than the wave that hit the bubble, because some of that wave is actually being reflected and bounced off instead of moving through. So the last little use of conservation of energy in waves that I want you guys to be aware of is something called interference. If you've played sports before, you know that interference basically happens when two players get in the way of each other, and wave interference is basically the same idea. It occurs when two different waves coming from opposite sides of a medium meet somewhere in the middle of the medium. When those two waves meet in the middle, the wave energy is combining as those waves overlap. This has to happen because of conservation of energy. So if I have, a wave with 10 joules of energy from the left and a wave with 5 joules of energy from the right, when those waves meet in the middle, that wave has to have 15 joules of energy, which means it has to have more amplitude than either of the individual waves. There's actually two more vocabulary words that you should be aware of here, something called constructive interference and something called destructive interference. Constructive interference occurs when you have like two up pulses moving towards each other or two down pulses moving towards each other, so two pulses that are on the same side of equilibrium. And when those pulses meet in the middle, they make an extra big wave. Okay, so an up pulse plus an up pulse makes an extra big wave, and a down plus a down makes an extra big. Those are both constructive, even though one of them is up and one of them is down. Destructive interference, as you can probably guess, means we've got an up pulse moving towards a down pulse. And when that happens, you can kind of think of it as having an amplitude of +5 and an amplitude of -5. It's not really realistic to say this has negative energy. There's no such thing as negative energy. It's just down energy. It's energy in a different direction than the up energy. But the interesting thing is when those two wave pulses hit each other, you get destructive interference just for the instant of time that those wave pulses would be overlapping. So in that picture on the left of the destructive interference, if this was an actual string and one person sent an up pulse on one side and another person sent a down pulse on the other side, and they were exactly the same size, when those pulses meet in the middle, the string is actually completely flat for a very, very short instant in time. The energy, though, isn't destroyed because of conservation of energy, which means that even though you can't see it in the string, the energy is still there, which means that those pulses will actually spontaneously regenerate in that rope and continue moving in the direction that they were always moving. So the up pulse continues to the right, passes through the down pulse, which continues moving to the left. If those two wave pulses are not exactly the same size in the medium, then when they meet in the middle, we end up getting just a smaller pulse that has less amplitude than the largest of the individual pulses when they interfere in the middle. So on that picture on the right, we've got a big pulse going to the right and a small pulse going to the left. When they meet in the middle, they make kind of a medium up pulse because the up pulse was bigger, but after that instant in time, they continue moving away from each other, and the big pulse keeps going to the right and the little pulse keeps going to the left. So a summary of these three important phenomenon that show conservation of energy. Reminder that the wave energy is demonstrated through the amplitude of the wave. Naturally, the amplitude of a wave decreases over time. It's because it's in our world we have usually open systems that these waves are moving through, and there's many different forms of wasted energy. If a wave hits a boundary between two materials, the amplitude gets divided based on conservation of energy. And you can actually add or subtract to an amplitude when a wave encounters another wave in the same medium. Just as a little bit of a random thought-provoking question, there is no such thing as wave interference when waves are moving in the same direction. Waves have to be moving in opposite directions to have that wave interference. You can never have interference with two waves in the medium moving in the same direction. If you can figure out why, you could come and explain to me why that can't be, and I'll give you an extra piece of candy. But in the meanwhile, you're done with your first three lectures of the day, and you guys can move on to your take-home quiz that you can work on Go ahead and use your Chromebooks if you need to do some research. I don't want you to have the exact same answers as your neighbors. You're welcome to help your neighbors, but try to pick a different kind of wave than the person that you're working with so that you can learn a little bit about different kinds of waves instead of all doing the same one. Thank you.